Welcome back to Mechanical Engineering Made Simple.
Today, we are taking a really critical look at the rolling bearing. I think it's fair to say it's the single most complex component in almost any machine.
Absolutely.
Yeah.
It operates at this terrifying intersection of intense load, speed,
Yeah.
really complex lubrication needs, and of course, the constant threat of contamination.
It really is the heart of the machine.
And if you work in any industry with rotating machinery, that unscheduled downtime, it so often points directly back to a bearing failure.
Hmm.
And I think the big mistake, the expensive mistake, is assuming that failure is just because you exceeded the basic capacity.
That is almost never the full story. So our deep dive today is focused on shifting your perspective from, simple replacement to actual root cause identification.
Wow.
We're using the authoritative structure of industry standards, specifically ISO 15243-2004E, to classify the damage. The mission is simple. If you can read the pattern of the damage, you can solve the problem permanently.
I love that idea, that the failure leaves a unique, like a path pattern or an imprint.
Yeah.
It turns every failed bearing into a forensic case study.
That's precisely right. This damage imprint is physical evidence. It tells the story of whether the failure started during installation or maybe during service.
And that's why you have to preserve it.
Exactly. Preserving that evidence through proper condition monitoring is it's a first step toward better reliability.
So let's start framing that story. What's the fundamental split? How do you start classifying bearing damage?
We use two major families to classify almost all post-manufacturing damage. You have the pre-operational damage modes and the operational damage mode.
A faulty start versus a faulty run.
That's the perfect way to think about it.
So pre-operational damage. That means the bearing was basically doomed before anyone even pushed the start button.
It was.
What are the key setup sins here?
These are all installation flaws. The big ones are incorrect shaft and housing fits. For example, if the interference fit is way too tight or if the housing seat itself is defective.
What do you mean by defective?
Well, maybe it's concave or convex or even slightly tapered when it should be perfectly cylindrical. The bearing ring gets physically deflected.
And once that ring is deflected, the internal geometry is ruined, isn't it?
Correct. The whole internal load distribution changes instantly. So instead of the load being spread evenly, it concentrates in these tiny little areas.
And it leads to spalling.
It leads rapidly to premature fatigue spalling,
Yes.
which is generally classified under that ISO mode 2.2 fatigue spalling.
And beyond just the geometry, what of the actual, the mounting technique itself?
Oh, faulty mounting practices are catastrophic. This could be physical damage during transport or storage, or the classic mistake, forcing a fit with the wrong tools.
The old hammer trick.
The old hammer trick, exactly. Hitting an outer ring when it's mounted in a housing, or vice versa. These actions can induce instantaneous internal cracks or massive false Brinelling, causing immediate failure right on startup.
Okay, so that's the faulty start. But what if the bearing survives installation and then it fails 6 months, maybe a year later? Then we're looking at operational damage.
Correct.
What categories are consistently responsible there during the service period?
The top two culprits in operation by a huge margin are ineffective lubrication and ineffective sealing.
Which I guess leads directly to contamination.
They're two sides of the same coin. After that, we look at operational misalignment, which might develop as the machine settles. And then you get into things like the passage of electric current and damage from static vibration.
Okay, let's dedicate some serious time to lubrication because it feels like it's the biggest single factor in bearing life.
It is.
When we say lubrication failure, a lot of people just think, oh, I ran out of grease. But you mentioned that too much lubrication is also a problem.
It absolutely is. Lubrication failure is. It's a complex topic.
Right.
It could be insufficient quantity, excessive quantity, using the wrong type of lubricant, or, just having the incorrect viscosity for the temperature and speed.
But hold on, why is excessive grease a failure mode? Wouldn't more grease mean more protection?
It seems counterintuitive, I know, but no. Excessive amounts of grease or over-greasing, it causes a rapid rise in operating temperature, especially at high speeds.
Right.
The bearing elements have to literally churn through this dense block of lubricant, and that generates immense heat. We call it churning.
And that heat just destroys the lubricant.
It degrades it chemically, which reduces its effective viscosity, and that leads directly to premature failure.
So quantity is one thing, but you said viscosity is king. Why is that one property so critical?
Viscosity determines the film thickness. And you have to think of that oil film not just as protection, but as a critical nanometer-thin layer of separation.
Like a cushion.
A cushion, exactly. If that film is too thin, the asperities, the microscopic high points on all the rolling surfaces, they start to contact each other. And that increases friction, generates more heat, and initiates wear and fatigue.
And if the machine's temperature fluctuates, say it runs hot and then cools down,
Yeah.
that protective film is changing too.
Exactly. And that's why we look at the viscosity index, or 6. High SI coils, you want at least 95 ideally, are recommended because they maintain their stability. They change less across wide temperature ranges.
So your protection doesn't just vanish because the ambient temperature went up.
You got it.
Okay, moving to contamination, which you said is tied directly to lubrication and sealing. What are the two types we're worried about, and how do they damage the bearing differently?
Well, we mainly deal with solid particles and liquid contaminants. Solid particles, dust, grit, little bits of wear debris, they cause indentations. Little dents, yeah. As a rolling element passes over a particle, it creates these tiny craters in the raceway. Those craters become localized stress concentrators, which is the perfect starting point for surface fatigue spalling. It's abrasive wear, pure and simple.
And what about liquid contaminants?
Liquids, water, acids, process fluids, they're the chemical enemies. They attack the lubricant itself, stripping its effectiveness and just tanking its viscosity. If water gets in, it can cause corrosive etching.
And that kind of damage often appears when the machine is idle, right?
Yes, the static etching phenomenon. It's a great example of a failure that happens when the equipment is turned off.
So how does that happen?
Well, corrosion often happens when the machine is idle because it allows the contaminants to pool in one spot. When you inspect the bearing later, you'll find these little damage spots, these etch marks, and they're spaced at exact intervals.
Corresponding to the rolling elements.
Exactly. The spacing matches the rolling element spacing. The simple fix for this is just to periodically rotate the shaft while it's idle, just to keep the surfaces wet and redistribute the load.
Let's shift gears from maintenance to the initial build. We said insulation is vital, but how do engineers get that hyper-precision you need, especially with certain bearing types?
The installation window is incredibly narrow, especially for bearings with a tapered bore, like CARB toroidal bearings or spherical roller bearings mounted on adapter sleeves.
Right.
These bearings are mounted by driving them up the taper, which intentionally reduces the internal radial clearance.
And if you drive them up too far?
If you have too much drive up on the taper, you completely eliminate that internal clearance. You go from having necessary movement to having damaging preload.
And preload is the enemy.
Preload is the ultimate enemy. It dramatically increases friction, which causes the bearing to overheat, and it can reduce its fatigue life by a factor of 10 or even more.
So the challenge is getting that exact right amount of clearance reduction. For cylindrical bores, it's a bit more straightforward. You use heating.
Yeah, temperature or hot mounting is the preferred method for cylindrical bores. You use an induction heater or precision oven to heat the inner ring. It expands, and you can just slide the bearing onto the shaft. No force.
So much safer and more accurate.
Far safer. And it's crucial to note that hot oil baths, they're just explicitly phased out of modern industrial practice. Too many safety, environmental, and contamination risks.
Okay, let's dive deep into the precision method for those tapered bores, the hydraulic drive-up. This sounds like engineering as a closed-loop measurement system.
It really is the gold standard for high-accuracy mounting. We use hydraulic nuts like the HMVE series, which are basically high-precision hydraulic jacks. And these nuts are fitted with two critical instruments, a calibrated pressure gauge and a dial indicator.
And why do you need both? Why not just one?
You need both to remove the guesswork of manual checks, like using feeler gauges. First, you pressurize the nut until the bearing hits a specific calculated starting position pressure.
Okay.
That pressure is determined by the bearing's geometry, and it ensures the bearing is perfectly seated. That's your reference point.
That's a baseline.
Exactly. And from that baseline, you then measure a very specific axial drive-up distance using the dial indicator. Because the physics dictates exactly how much the clearance reduces for every nanometer of axial movement, measuring the distance guarantees you get the precise clearance reduction you need.
Without inducing that destructive preload.
Without any destructive preload, it converts a force problem into a highly accurate dimensional measurement.
That level of rigor is really what separates basic maintenance from engineering reliability. So let's talk about monitoring. What signals warn us that something has gone wrong during operation?
Noise and vibration. They are the canary in the coal mine. Analyzing the frequency and the pattern of the sound can tell you the root cause. For instance, a persistent low-frequency rubbing noise. That often means you've got misaligned housing seals.
Or maybe a loose lock nut tab hitting the cage.
Exactly.
What about a high-pitched sound, a scraping or a sliding sound?
That's often skidding. It happens when the rolling elements are sliding instead of rolling. Maybe the bearing doesn't have enough load on it, or the lubricant you picked is just too stiff for the operating temperature.
And then there's the really modern failure mode we see more and more. Electrical erosion or fluting.
This is a massive issue, particularly in variable speed electric motors running on frequency converters.
Yeah.
If the grounding is inadequate, the current finds the path of least resistance.
Straight through the bearing.
Straight through the bearing. As the current arcs through that thin lubricant film between the rolling element and the raceway, it causes these microcraters. It's like thousands of tiny arc welds.
And over time, those microcraters create that distinct washboard look we call fluting.
That's right. Fluting is a visible pattern of axial grooves. Looks just like a washboard on the raceway. It quickly leads to heavy vibration and premature wear. And even using insulated bearings won't help if the rest of the system isn't properly grounded.
Let's circle back to what I think is the core lesson here.
Yeah.
Sometimes the bearing is the victim, not the cause. Our sources had a couple of really high-impact case studies about this.
Yes, these are vital examples of system failure. Take the out-of-round housing. If the housing bore is oval, even just slightly, it mechanically pinches the stationary outer ring.
So if the outer ring is stationary, it's getting squeezed in two spots 180 degrees apart.
Correct. And that localized pinching is basically inducing a massive targeted preload.
I see.
That preload creates high friction and high heat, but only in those two spots. This leads to adhesive wear, rapid lubricant breakdown, and premature failure, all because the housing, a non-bearing component, was made wrong or deformed over time.
And the spacer mistake, the train derailment case study, that's even more dramatic.
Yeah.
It shows how one tiny error in an adjacent part can lead to total catastrophe.
It's a chilling reminder. In that case, a critical spacer was installed that was just a little too short. And because it was too short, the bearing inner rings were never properly clamped by the lock nut.
So they can move around.
It could shift. And that induced heavy internal axial loads and excessive shaft bending. The resulting friction and internal stress led directly to bearing seizure and catastrophic fracture.
It's causing a derailment, just from a small spacer.
From a small spacer. It shows how precision in every single adjacent component is absolutely necessary for the bearing to survive.
So whether it's thermal failure, electrical erosion, or mechanical fracture, the message is the same. Vigilance and analysis are non-negotiable.
Condition monitoring devices, things like vibration analyzers, are essential to detect this damage early. But simple temperature checks are vital too. Anytime you see a temperature spike, especially a sudden rise right after startup or immediately after a relubrication cycle, you have to investigate. It's often the simplest and earliest sign that something's wrong.
This deep dive has really synthesized the critical layers of knowledge needed for rotating equipment. To maximize bearing life, it seems you have to master three areas: the precision of your installation, the correct volume and viscosity of your lube, and just relentless contamination control.
And I think the critical takeaway for you, the listener, is to always look upstream. When you pull a bearing that shows fatigue spalling, don't just automatically jump to capacity issues. Ask yourself, is this spalling the secondary damage? Is it the result of a much earlier primary failure, maybe an unnoticed misalignment during installation that caused preload for years, or a bad seal that's been slowly letting in corrosive fluids?
The spalling is the consequence, not the crime.
Exactly, that's the mindset.
That's it for today, Design Junkies. If you're getting something out of this, follow the podcast, leave a review, and don't forget to check out our YouTube. It helps the whole family grow, learn, and build better together. A family that solves together, stays together.